For this example, we're going to be determining where the function that's given here that looks like a pretty complicated rational function, we want to find out where it's positive and where it's negative. Now, this complicated looking rational function is actually the form the second derivative of a pretty simple looking rational function would take. And so in calculus, when you are solving these nonlinear inequalities, those that you're solving are going to be derivatives. They're going to be first derivatives and second derivatives. And so the first challenge really to solving the nonlinear inequality is to get the function in a form that you can work with. And so we need this function to be in a nice factored form where the top is factored and the bottom is factored. And right now we've got the bottom nicely factored, but the top needs some cleaning up. And so I wanted to demonstrate how you can be smart about the cleaning up part of this rational function. So what we are looking at here is what would have been used as a quotient rule a couple of times to get this function. And so we see there that we have that subtraction sign from the quotient rule that's at the that's on the top. And so the overarching thing that we have on the top is a term that is before the subtraction sign and a term that is after the subtraction sign. And what we could do is just multiply all of this out and then try to figure out how to factor it, but that is not the wise way of tackling this. What a smarter, more efficient way of tackling this cleanup is to look both before and after that subtraction sign to find out what your greatest common factor can be. And so when I'm looking at that, I see that I've got, well, first of all, I'm going to draw my fraction bar. I'm going to go ahead and write the denominator because I'm going to be focused so much on the numerator that I'm going to forget the denominator if I don't write it. So I'm going to go ahead and write it. Now, take a look at the two terms on the top. I see a negative 2x that's in the first term here, but it's also in the second one because I've got a 2x there and I've got that negative sign that I have to play with too. So I'm going to pull out the factor negative 2x. But the other thing that I see is this factor x squared plus 1. It appears both behind the subtraction sign and two copies of it appear before the subtraction sign. And so the best I can do is pull out one copy of that. And that would be my greatest common factor of the things that are separated by the subtraction sign. So once I've pulled out my greatest common factor, we've got to figure out what's left over. So I'm going to do a big bracket here so I can keep track of what my common factor is and then what's the leftover part. So I pulled out the negative 2x and one copy of the x squared plus 1. So I have one remaining copy of the x squared plus 1 that comes in front of the subtraction sign. But now what comes behind the subtraction sign, I actually pulled the subtraction sign out. So I pulled the negative part out along with my 2x. And so I'm left then with the plus instead of a subtraction. So the other things that are left there are the factor 1 minus x squared. And I've got the factor of 2 sitting there also. Everything else got pulled out to the front. And so I can go ahead and clean up what's in the big brackets by distributing gathering like terms to finish up my factorization here. So again, I'm going to draw my long division line, and I'm going to remember my x squared plus 1 raised to the 4th power. It's going to be there on the bottom. And then I have my negative 2x, my factor x squared plus 1. And then here in the brackets, I've got x squared plus 1. I don't really have to have that in parentheses as we're just moving through trying to clean up the addition and subtraction there. The thing that I needed the parentheses for is the next thing because I've got a 2 that needs to be distributed across what's in parentheses. So that would be a plus 2 minus 2x squared. Okay, so now I've gotten rid of my parentheses and I'm ready to gather my like terms. So again, I've drawn my division sign. I've gone ahead and put the factor on the bottom and copied over the factors on the top. But now we're ready to have completely cleaned up what's in the brackets there. I have an x squared and a minus 2x squared. So that would be a minus x squared overall. And we've got a 1 plus a 2, which would be 3. So I'm going to go ahead and write this as the constant 3 minus 1x squared. Okay. So the last thing that I would do to clean this up would be noticing that we've got, oh, you know what? I made a copy error here too. Let's fix this copy error. I'm so used to thinking about denominator squared for the quotient rule that I forgot that this was actually the quotient rule applied twice. We've got x squared plus 1 not squared, but to the 4th power. That was a copy error. Now let's look at what we have. That x squared plus 1 factor, there's one copy of it on the top, there's 4 copies of it on the bottom, so we could cancel one of the copies out, and so that leaves me with my x squared plus 1 to the 3rd power on the bottom, and then it disappears on the top as it canceled. Okay, so our top there is negative 2x times the factor 3 minus x squared, and then the bottom is the x squared plus 1 raised to the 3rd power. So we've done all of this algebra, and now we're finally prepared to actually answer the inequality question. Where is this positive, where is it negative? So here's our cleaned up function, and we're looking at where is it equal to 0, so that we can, and where is it undefined, so that we can use the intermediate value theorem to check all the intervals in between. So this rational function is 0 where the top is equal to 0. So that would be the factor negative 2x equal to 0, or the factor 3 minus x squared equal to 0. So we solve each one of these. The first one, we divide both sides by negative 2. 0 over negative 2 is still just 0. And then this other one here, we would add over the x squared to both sides. And then we have to square root both sides. And I'm going to flip where the x is on the side of the equal sign. But when we square root both sides, we've got to have a plus and a minus. And then we would have the root 3 there. So those are the 3 roots for where f is equal to 0. We need to look at where is f undefined, and that's setting the bottom equal to 0. And that bottom equal to 0, it's really just a single factor copied 3 times. So we're really looking at just the factor x squared plus 1 equal to 0. If we go about trying to solve this, we've got x squared equal negative 1, and there's no solution there. X squared would be always positive, so there's nothing that's going to allow us to plug it in and get a negative 1 there. So we don't get anything from that factor. So we put these values on our number line for f. We're going to go ahead and label it here f because we got our we got our cutoff values from the function f equal to 0 and undefined, and we're going to be testing it into the function f also. So we want to make sure that we've got those values there. Get them in the right order. We didn't lose any. And now we've got to pick test values in between. So let's see. I know that the square root of 3 would be less than 3, so I could choose there negative 3 being the other side here and positive 3 being the other side. I would also know that the square root of 3 would be more than the square root of 1, which is 1. So we're talking about those being test values. We could choose 1 and negative 1 on either side of the 0. So now we've got 4 intervals here that we've got to test, and we've got to test them into the original function f of x here because we are trying to assess the positive and negativeness of that function. And so each one of these is a fraction. But look at the bottom, x squared plus 1. X squared is always positive. Adding 1 keeps it positive. Cubing it keeps it positive. So no matter what your test value is, your bottom is always positive. So it's really about what's happening on the top. So negative 3 plugged into the negative 2 times x would be negative 2 times negative 3 would be positive. And then we've got negative 3 plugged into the last factor. 3 minus, in parentheses, negative 3 squared would be like 3 minus 9. So that's going to be a negative. So overall, we've got a positive, negative, another positive. So there's only an odd number of negatives, so it's negative. Moving on to the next test value of negative 1, we've got negative 2 times negative 1 would be positive. We've got a 3 minus a negative 1 in parentheses squared would be 3 minus 1, which would be a positive. And so 3 positives there overall give us positive. Moving to the next test value of 1, we've got negative 2 times positive 1 is negative. And we've got 3 minus 1 squared would be 3 minus 1, which would be positive. So one factor that's negative gives us a negative overall. And then our last test value of 3, negative 2 times positive 3 is negative. And 3 minus 3 squared would be 3 minus 9 would also be negative. And we're looking at now an even number of negatives. So negative times negative on top would be positive over the positive is positive. So we've assessed our signs, and we just need to write our conclusion here. So we've got positive between negative root 3 and 0. And we've got positive again from root 3 to infinity. Negative, we have, starting all the way at the left, we've got negative infinity to negative root 3. And then we've got this interval 0 to root 3 in the middle for negative. And so we again see that the endpoints of these intervals are never ever going to be test values. They are only these switchover values where the function was either 0 or undefined. And that each interval we assessed was either in the positive category or the negative category. There's no overlapping. We just had to look at the individual intervals and put them in the right category to get our answer.